Here we are back again, continuing our discussion of clustered and non-clustered indexes and the consequences for query processing. So we have seen in the presence of non-clustered indexes, bitmap heap scan and bitmap index scan, that pair of operators can give some relief there and can help us to still evaluate queries efficiently. But if your workload really critically depends on the speedy evaluation of a particular predicates, or as we will see later, other operations that rely on order, then it might be the time to consider a really strict and a really impactful reorganization of your database, namely to turn a non-clustered index that's currently supporting your predicate into a clustered index. That would be, of course, ideal if you could do that for all of our indices, but as you know, only a single index for a table can be the clustered index. The table's rows can only be ordered and organized regarding a single column. Okay, so if that index I is really crucial for the speedy performance of your workload, then it could be an option to decide to really physically reorder the rows of the underlying table to match the order of index entries in your index I. This will of course turn I into a clustered index. Okay, so we will really reorder the rows on disk inside the heap file. We will reorder the rows to match the order of the index entries. This is a really far-reaching reorganization of your database, and of course it comes at a cost. Any indexes that might have been clustered by until now will of course turn into non-clustered indexes after we have performed this physical reorganization. So that's really a very important physical design decision to make: which indexes to turn into clustered indexes, which indexes to select and to elect to be that one index whose order matches the order of the underlying table. All right, you can do that in PostgreSQL using the cluster command. All right, so we would reorder the rows of row T so that they match the order of index entries in index I. Okay, so cluster T using I would be the command. There's also the verbose option that will tell you a bit about the statistics and the timing of this operation, but it's not crucial. Cluster T using I is the command. Once you've performed this operation, indeed, all the rows inside T will match the index entry order in I. Subsequent updates to T might destroy this perfect clustering, this perfect order coincidence again. So it's not the case that inserts or deletions into T, in particular inserts, will now perform ordered inserts so that they match the index order and thus the index column order. This is not the case. Any subsequent updates may destroy the perfect clustering, and maybe from time to time it would then be wise to recluster T to really re-establish this perfect coincidence of row order and index entry order. And you can just do that by performing the cluster T command. Cluster remembers the last index that was determining the row order here, and simply providing cluster T will recluster T to match the order that we have established in the first place. Okay, so that's the cluster command, and the idea of reclustering a table, or to reorder the table to render an index I clustered. And so let's play with that over in the PostgreSQL terminal. Okay, so here we are in our playground situation again. It's again time to query the index table regarding this index condition over column C, and the indexed _C index is a non-clustered index. The situation is just like we've seen in the previous videos. And when we perform this query, we will of course see the bitmap index and heap scan pair. There you go. All right, so 3,531 matches have been found on 2,964 different pages. That's a really lousy ratio of only 1.19 rows per page that have been found. That's no surprise because matches regarding this index condition are found all over the place. Okay. So that's the situation of the bitmap index scan and bitmap heap scan in the situation that the index C index is not clustered. Okay. So we will now recluster, or cluster rather. We will now cluster the index C index, and that means we have to reorganize the order of rows in the heap file for our table indexed. Okay, this is really a really impactful, far-reaching reorganization of the table data file, and as we can see in a second, this actually means that PostgreSQL will rewrite the entire heap file. It will throw away the old heap file, and it will rewrite the heap file for the data for the data file for the index table from scratch. Okay, so let's see before we do the clustering here, the file that holds all the rows of our index table is 76466. So let's keep a record of that. I think this might change once we perform this command. Please reorganize the order of the rows in the index table to match the index entries in the index C index. Okay, so let's perform that command. Okay, doing some work here. All right, so that's it. Okay, did take some time. Oh, it's not done yet, I think. Okay, so there we go. Oh, it took 15 seconds. So that's a major reorganization, I would say. Let's see what we've got now. If we now look at the indexed table, and this command will also list the indexes defined on that table, then we'll find information about the table and also about its indexes. And indeed, the C index is now the index that prescribes the clustering of the rows inside the table. Okay, so this has been performed just as we wanted. And indeed, this led to a complete rewrite, to a from scratch rewrite of the heap file for the index table. Let's see. So that's a new rel file node. It's 76476 and it has been 76466 before. Yeah, this is an entirely new file that now contains the rows of the index table in C order, in column C order, matching the index underscore C index. Nice. We can actually see that. We should be able to see that if we now query the rows of the index table and order them by the C column, all right, then we should see that also the row IDs are ordered. So the order of the C values, this is the order of the index entries, matches the order of the rids. This is the physical order of the rows in the file. Okay, so let's see. We can have a peek at the very first few entries, which start with C -1. These are the smallest C entries that we have. There's several of them, and all of them cluster at the beginning of the file. You see, this is the first page, and the first slots, they all carry the value, the rows that have minimum C values. And it's just like that at the end of the file. Let's see. So these are the maximum values. These are the maximum C values, and they all cluster around the end of the file. All right. So indeed, this is a file that is now clustered according to the C column or the index underscore C index, just that we wanted. Okay. What we could also do is now determine the so-called clustering factor. Okay. This is the ratio of rows for which this ordering restriction, the ordering criterion, holds. The number of rows that are indeed that are indeed in whose physical placement, this physical placement is dictated by their C value in this particular case. Okay, so if we perform this analysis for the C column, so is the order of rows indeed compatible with the C column values, then we should find that this is indeed the case for all of the rows we have just reclustered. All of the rows have been placed in the heap file regarding their C value. So C values and physical location in the file coincide. And if we perform this query, and I will show you this query, as you can see, as it will be a future homework assignment. So let's evaluate this particular query. This has been the analysis regarding column C. Then we see indeed clustering factor is 100%. So for all of the rows, their location has been determined by the C value. So very good. If we perform the same analysis for regarding the A column, does the physical location of the row in the file reflect the A value or the ordering of the A values, then we will find a very different answer. Okay, so it's, well, for almost no rows out there is their A value coinciding with their actual physical position inside the file. This is the so-called clustering factor, and the clustering factor may decrease from 100, from this perfect 100, once we perform updates on the file and we insert rows with some C value somewhere at the end of the file, but they should have been sorted to the beginning of the file and so on, so that clustering factor might reduce over time. If it reduces too much and the ordering of the index entries and the physical order of the rows in the file go out of sync, then maybe it's time to recluster the table and the index. Okay. All right. So now that we have clustered the table regarding the C index, let's see how this query performs now. It should see some effect there. Before this operation, we found the matching rows all over the file. Or before the clustering, we found the rows all over the file. And yeah, well, because the C value didn't determine their physical location. It should be different now. We are looking for a very particular C value, and all of the rows, that's our hope, will be found physically adjacent in a very small region of the underlying data file. Let's see whether we can actually find that when we evaluate the plan here. Okay, so that's still, of course, 3,531 matches, but all of these are found on only 34 pages. Okay, so that's a completely different picture. Our file has about 9,300 pages, I think, but all of the matches are actually being found on only 34 pages. So that's a very efficient access for all the rows that match the index condition. The sequential scan that is being performed by the bitmap heap scan can skip almost the entire file. And there's only very few pages, 34 of them, that actually carry valid entries here. Okay, so before that we had this very disappointing number of 1.19 rows that matching rows that we found on one page. Now we found like more than 100 rows on each page. So 3,531 matches are only found on 34 pages. That's a good ratio. Okay, if we now give PostgreSQL the time to really analyze row order, take your time, analyze row order, and try to see which indexes really coincide, which index entry orders really coincide with the physical row order, and this is being done by this analyze command, then PostgreSQL will notice that these bitmap index scan and bitmap heap scan may indeed not be necessary anymore. This is such a perfect cluster situation that a normal index scan that goes without any bitmap construction and so on, a single pass index scan, will probably be the better choice here. So let's invest a few seconds so that PostgreSQL can analyze the physical row order in the index table and match it with the present indexes. Okay, All right, so 1.3 seconds spent there. I think it's 1.3 seconds very well spent, because if we now repeat this query, we will see that the PostgreSQL now decides, okay, no bitmap index and heap scan necessary anymore. We can just use the perfect index scan method, because we are in a fully clustered situation. Let's see that. Yes, indeed, index scan has been performed. No need for bitmap index scan in the clustered situation. All right, so much for the impact of clustering on index scans and the speedy relation of predicates. So let's draw a line here and now switch gears and talk about the dynamic update operations in BitPath trees, the insertions and the deletions. And because this is a different topic and because my voice is getting rough, let's cut the video here and restart with the next video when it gets to the B tree updates. See you then.